Okay, so we're going to continue with linked lists, probably finish it up today, and then move on to list-based data structures like stacks and queues. Just to remind ourselves of what we were doing last time though, remember that we've got a linked list here where elements are stored in nodes rather than in an array. And so we've got the head, and usually we call this the tail over here, right, the last one. But otherwise, our list implementation is only keeping track of the head. Why? Because from the head, you can always get to any other node by simply traversing, right? And so we had set up this experiment over here that we'll come back to. But otherwise, now what I've done is I've created a linked list, my linked list, and I've added elements 10, 20, 30, and 40, which are going to look exactly like this. And so that's going to be our test bed for completing the rest of these methods. Remember that we had this general getNode method at a particular index. We made it private though because we didn't want a leaky abstraction to leak to the outside world that everything is being stored in nodes. We have this add element which simply adds it to the end. So we create a new node if for one of those corner cases here that if it's already empty, then that's going to be our new head, and so we increment the size. Otherwise, what we need to do is we need to find the last one, and I'm using my helper function, my convenience function there to do that. I'm getting the last element there, so the next to last, the last element, so that I can go ahead and tack on this new node to the end. And then of course I increment the size. We still have to do remove the last element, but we've got get element at index, and we're doing some error bounds checking here. We've also got get size is empty, replace element at a particular index, we did that one. Remove element at index and insert element at index. Right? So that's where we're going now. Let's go ahead and start at the top. Let's go ahead and do remove the last element. Right? So let's think about this in terms of this picture over here. Okay. First of all, the very first thing that we need to do, of course, is find that last element. Just let me make sure that this is right. Yep, we're good. So if you have any questions, go ahead and post to the live stream here. Otherwise, what we need to do as a first step is we need to find that last element, right? And once we've found that last element, then we can kind of remove it. Except that what are we going to have to do to make it so that that last element is gone? We're going to have to take this second to last element and then, make it point to null. So I don't actually want the last element. What I want is the second to last element. Once I've done that, to remove the last element, all I need to do is, is make it point somewhere else. Except that this sounds kind of familiar, right? Didn't we already do? We've got replace remove element at index here. Right? What if instead of doing all this manually, what if I called that method? This dot remove element at index, and then what's my last index there? So if this is my list here, 0, the indices here are going to be 0, 1, 2, and 3, right? And it's of size 4, then what's the last element that you want to remove? This dot size minus 1. So I have shoved off the responsibility of implementing this function to another function, right? So let's actually go ahead and do that now, right? Remove element at a particular index, okay? So now let's come over here and think about this more generally. Back up, right? If you want to remove, say, the last element, right? Then what would you do? You would get the one right before it and then make it point to null. In other words, the thing that points to. More generally, if you wanted to remove this element, what would you do? You would circumvent that element by taking the one before it and making it point to the one after it. Once that's gone, then you pull the chain tight because it's a linked list, then that is effectively gone. Think about another corner case here. What if we wanted to remove that first element right there? Right? So there is no previous element to get, right? To circumvent it and go around it. Instead, what do we need to do? We need to make the head point to the second one instead. So let's take care of all of those all together here. Right? First of all, if you ask for something that doesn't exist, I'm going to throw it right back at you, right? In other words, I'm going to go ahead and grab this code, and if you want to remove the element at a particular index, even though it doesn't exist, I'm going to go ahead and throw it back at you as an illegal argument exception. If you try to remove something like a negative value, negative index value, or something that exceeds the size or is equal to the size, because if there are 4 elements, what is it? 0, 1, 2, 3. Right? Can you remove the element at index 4? No. All right. Let's take care of some corner cases here. Else if index is equal to 0. Right? Here we're going to want to remove the head. Right? Now that's one of those corner cases that we just visualized over here. How are we going to remove the head? Get rid of this first element right here. We're going to want to make the head of the list point to the second one. Right? So let's go ahead and do that. Right? This dot head is equal to this dot head dot get next. Right? Now normally, or I would have to be very, very careful here about whether or not the head is already null. Because can I invoke the get next method on a null object on line 97? No. Are we okay though? So think about when the head would be null, when it's an empty list, when the size is 0, right? If you want to remove something at the head of the list, index 0, when size is 0, guess what? 0 is greater than or equal to, 0 is true, and we would throw that back at you as an exception. So we have a good assurance here that the head is not null. Once I've removed the head, what should I do with my size? Minus, minus. Right? Else. These are all of the other cases here. Right? Now, oh yeah, by the way, when we remove an element, we're actually returning the element that is stored in that node. So what I'll do is I will save that off. T x is equal to this dot head dot get element, and then I'll go ahead and return it at the end of that block right there. We still need to do the same thing over here. So I will get the, suggestions on this. Right? So I know that I'm not removing the head. I know that I'm removing maybe some internal node here, this one, or this one. Right? How are we going to do that again? Again, let's go ahead and think about this one right here. I want the previous one, and then I want to make the previous one point to the next one. So if I'm using the terminology here, previous, current, and next, then let's go ahead and start by getting those 3 nodes. Okay? I have a method to do that, don't I? Node t previous is equal to this dot get node at an index minus 1. Right? That's the one right before it. What about the current? That's going to be at the current index. And then what about the next one? We want to line these all up. Index, index, plus 1. 1, there we go. But now think about this, right? Say that there are 1 million elements here, and you want one right in the middle or something like that. Say 2 million elements, and you want the millionth element. What are you going to do to get all 3 of these? You're going to start at the head, traverse 1 million nodes just to get the previous one, right? Then you're going to start at the beginning again on line 103, traverse 1 million nodes just to get the current one, and a third time to get that third one. Is there a better way of doing this? Yeah.
You use previous to get the next node.
Ah. There we go. Dot get next. And then use the current to get the get next. There we go. Now, am I doing this 3 times? Nope. I'm only doing it once, and then going to the next one, and then going to the next one. And then I've got a story to tell you about a painter that we'll talk about here in a second. All right? Okay, so now I've got those nodes. Once I've got those nodes, what am I going to do? I'm going to make the previous point to current. Or it points to the next, excuse me. So previous dot set next to be next. And we've just gone around the current node. Why am I keeping track of the current node? Because what I want to do is I want to return current dot get element. Right? So all I'm doing is circumventing this, and then I still have current here, so I end up returning 30. Let's test it. Over here I've got demo. I've added 10, 20, 30, and 40. We'll print it out to make sure it works. We'll print it out again after I've removed a number. Numbers.remove element at a particular index. Let's go ahead and start with something that we know should throw an exception, -1. And we'll also actually return it. So let's make sure that we're getting the value back as well. I'll go ahead and print out the list and then print out the thing that was removed. So we should expect that this is going to throw an exception, and it does. If I go the other direction, right, 4, that should throw an exception on the other direction, and it does. Now, let's start testing things in between. This is going to remove the head. It's going to remove 10, so we'd only have 20, 30, 40 left. That works, and it returns 10. The next thing we should test is, can we remove the second element? So 10, 30, 40 is what we would expect, and it works. That also works. What about the last one? That also seems to work. Right? Now this is all just ad hoc testing. If I were doing this in real life, what I would do is I would code this up as a JUnit test suite so that it's repeatable, right? And so that I don't have to change, check, change, check, change, check, change. Then I go back and I make a change, I have to do it all over again from the beginning. Right? Nope, if you coded it up in a JUnit test suite, then you can run it as many times as you want without having to do this over and over and over again. Okay? You know what? Remove element at index is being called by remove the last element. So let's make sure that that actually works as well. We do know that it works because it just calls remove last, come on. It's a void function? Okay, fine. We can change this, otherwise, that's all right. I'll just go ahead and leave it as is. We have a tight mismatch with our interface, and I don't want to go changing that because that'll break a bunch of other things, and I don't want to focus on that right now. Right? So what else do we have? First of all, how do I know what I still need to do in this class? Go looking around and is that implemented? Did I finish that? Is that implemented? Did I finish that? What does a good programmer do when they don't want to do something immediately? They put in a to-do. Those little blue dots right there, blue dashes or whatever, right? They should be to-dos. Oh, no, sorry. Those are breakpoints. Is this another breakpoint? Yeah, that's a breakpoint. All right. Sorry, get rid of that breakpoint. There we go. Instead, you go over to your tasks, right? And unfortunately, it's going to list all the tasks in my entire workspace here. But otherwise, you can collect all of these, right there. So there's the next to-do. Is that a to-do? Is that the only one? Yep, it is. So I don't know, did I have, what did I just, oh, I don't want to do that. Get element, there we go. All right, I don't know what I just erased to get rid of that other blue thing there. Might not have saved it, that's it. All right, so let's go ahead and insert element at an index. Let's again come back to our little example here. Now, let's think about corner cases. You could insert at the very beginning, right? In which case you would need to, say, create a brand new node over here, say 42. That's initially pointing to nothing. Right? And then you would need to make the head point to this new one, and you would need to make this point to the new head. It sounds really familiar though, right? So, yeah, go ahead. Suggestion? Or? No. Okay. All right, so let's go ahead and follow the same pattern that we had before. First of all, we're going to check. Did you give me a correct index here? Now, wait a second. Insert element at index. If we've got 4 elements, you can insert it at 0, 1, 2, 3. What about inserting it at index 4? Should that be okay? Yeah, that's just inserting it at the end. So now that's going to be greater, strictly greater than the size, okay? If the index is 0, maybe that's a corner case, that's a special case where we insert something at the head. This dot insert element at, oh, okay, nope, I thought we had done add element to head or something like that, but apparently not. So add a new head node. dot, dot, dot. Else, add somewhere in the middle, dot, dot, dot. Okay. Add a new head node. How do we do that? Well, first of all, we need to create the node. Let's see. Oh, you know what? I'm now remembering that we had a problem up here. I decremented the size here once, but did I do it down here? Nope, so let's do it there, all right? That's actually not gonna manifest because I've already done the other testing, but I know it will be a problem when I post the code. Anyway, let's go ahead and create a new head node. New head node, right, is equal to new node, and we'll put in X here. This dot head is equal to the new head node. There. Did that work? Let's think about that. So I created a new node just like this, and then what am I doing? I am making this point to this.
How did you do it for insert?
Oh, how did we do it? Do we have another insert method here? I forget.
Yes, I think it's talking about remove element.
Yeah, that remove element, right? There's an add element that adds it to the end, right? There's a get node element, et cetera, et cetera. But how do we add a new node to the head? Right? This is going to be adding at the beginning, not adding at the end. Right? So this is the picture that we've drawn so far. What's happened to all of these other elements over here? Yep, they're lost. Right? So what do I need to do first before repointing this head over here to this new node? New head node dot set next is equal to the old head node. There we go. This dot head. Then you can reset this dot head. Okay. All right. Now add it somewhere in the middle. So again, let's visualize this. If I'm let's undo. There we go. I want 42 here. I want to insert it, say, right here. Right? In other words, what I'm going to do is I'm going to want to make sure that I'm getting this previous node and making it point to this node. And then instead of pointing this to null, I'm going to make sure that I point it to this one. Right? In other words, severing this link right here. Pull the chain tight, and now you've got 10, 20, 42, 30, 40. Right? That means that, again, same pattern as before. I want the previous and the current. And now do I need to worry about the next? No. So, yep, because we're inserting, exactly. And I don't mess around with any of its references or pointers. So let me go ahead and get those two nodes. Node t previous is equal to this dot get node. You see how useful it was to define that function for me, right? Now everything else falls into place really, really easy. Current is equal to this dot get node of index, except that, yeah, why are we doing this twice? Right? So previous dot get next. There we go. Oh, and by the way, before I do anything else, what do I need to remember? This dot size plus plus. In fact, I'm not going to forget that down here. I'm going to go ahead and add that immediately. There we go. So I've got previous and current. How do I do some pointer manipulation here to get previous to point to this new node, and then this new node point to the current? Well, I do need the new node first of all. So it's not the new head node, but just new node. Right? There we go. So I need to make previous point to the new node. That is previous dot set next to the new node. And then I will make the new node point to the current. So this dot, or not this, but new node dot set next to current. There. That's it. Yeah.
I guess there isn't a problem if you like set the new node, like setting previous to new node and then pointing to current. Like, are you not going to lose the rest of the list?
Not I mean, no.
Okay.
That's a
I
good
know
question.
There was a
Is there, in that one instant, would the garbage collector say, okay, you lost everything? I don't think so, because you still have a reference to previous here.
Okay.
And so, wow, that's a good question for like a race condition of some sort where, okay, well, no, you lost it temporarily. Well, no, you can't lose it temporarily. You still have this reference here. And so somebody, a local variable in this context is still referencing it. The garbage collector is not going to be that efficient anyway. All right, so let's go ahead and make sure that this works. Still print everything out, numbers dot add element, or what is insert element at index. And we'll go ahead and insert 42. Again, test everything. Make sure that the bounds checking works. We should expect an exception here. We should expect that if we add it to the beginning, that is basically inserting it at the head. So 42, 10, 20, 30, 40. This would be 10, 42, 20, dot, dot, dot. This would be 10, 20, 42, 10, 20, 30, 42, 10, 20, 30, 40, 42 at the end. And then here, finally, we've gone too far, and that's going to be an exception being thrown. And again, this is why I would do this in a JUnit test, because not only would I have like 5, 6, 7 tests ready to go here, I would put them in a loop so I didn't have to write and cut and paste 5 different tests. Right? And they all pass, or they don't, if one of them fails, then they all fail. Right? And oh, I already took out my to-do. I should have waited until I was done and tested to make sure that I take out the to-do. Otherwise, everything's great. Right? All right, so let's go back to the original demonstration that we were running here. I am pretty sure that everything works. Remember this original demonstration? Oops, undo that, undo that. No, no, come on, undo, there we go. What we're gonna do is we're gonna take 100 integers, 0 through 99, and we're simply just going to add them, right? Remember that we tested this with an array-based list, and then we looked at a linked list. Is it better or not, whatever, right? Let's go ahead and look at a linked list first of all, and we're going to be adding an element, not to the end, but let's go ahead and add it to the start. Or insert element at index, and so I will be added to I, right? Sorry, 0. Right? We're always going to be inserting at the beginning. Right? So I've set up a table here where we're going to time this. So here's my linked list, and here's my array-based list. Here's the insert at the start operation. Here's the insert at the end operation. And we're going to go up by orders of magnitude here. We're going to start at 100, 1,000, 10,000, or 100,000, and 1 million with a question mark, because we're going to predict without actually running that stuff. So I've set this experiment up, and of course, if you really wanted to do this in real life as an empirical study, you'd isolate it and you'd do it 100 times and then take an average. We're not going to be that rigorous. So there's, oops, we don't want to actually print it out, sorry. I don't want to see that. There we go. All right. So initially it's empty, and it only took 0.001 seconds. So I'm going to note that down, oops. I won't show it to you because you see it right there, 0.001 seconds. Now let's go up by an order of magnitude, 1,000. Okay. Now, if it's 10 times bigger, I would expect it to be 10 times slower. About that, right? If it's 10 times bigger, I would still expect it to be 10 times slower. So in this case, it's going to be what? 0.02 seconds? Oops, come on. Okay, so it's still staying at 0.002 seconds. We haven't seen a big jump in complexity yet here, right? There we go, 0.011 seconds. And I'm comfortable here actually going up here with 1 million, right? And yeah, orders of magnitude, right? Again, it was what before? It was 0.01 seconds. And so when we go up by an order of magnitude, now we're starting to see that expectation, that it's going up 10 times as big. Right? 0.193 seconds. Right? There. There are the results of our experiment so far. Now, what about insert at the end for the same thing? Still a linked list here. I'll kick this back down to 100. Right? And I'm not going to insert it at that index anymore. Instead, I'm going to insert it at, say, well, I can just go ahead and do that, right? So you insert at the end, right? All right, so 100. Okay, it's very, very comparable. In fact, it's exactly the same as we saw with insert at start. So I would expect maybe this is going to end up being the same exact kind of behavior. 0.003, right? Which is very comparable to the previous one. Now let's go up to 10,000. Right? So if this is going orders of magnitude up, then this should be about 0.03 seconds. Ooh, wow, a little bit of a jump. Maybe that's just because we're not doing a proper experimentation and we're not doing this multiple times and taking an average. Okay, it's just a sampling error. Let's go up to 100,000. Now remember, this took 0.011 seconds inserting at the start. (13 seconds), 13.52 seconds. Let's go to our chart here, and let's start thinking about how these things are going up. So if I'm going up orders of magnitude, 10 times as big, 10 times as big, 10 times as big, right? This one kind of tracked with that, right? You know, it wasn't exactly this in lower order values, but once we got up to 100,000, it was going up by an order of magnitude as well, right? That this was going up by 10 times, this was going up by 10 times, about, right? Do the same thing here though. Is that 10 times as big? No, what is that about? 100 times as big. Right? So let's kick this up to 1 million, run it, and while we're waiting, if that, what is this? This is almost 100 times as big too, right? About 50 times as big. Right? Let's just suppose that it's 100 times as big. Let's predict. How big will this be? 100 times 13 seconds is going to be 1,300 seconds, and what's that going to be?
Hour.
1,300 seconds to hours. Google says okay, let's go to minutes then instead. 21 minutes? All right, so about 20 minutes. Okay? And so I'm not even going to bother doing that because we're not going to sit here for 20 minutes. All right? No, absolutely not. Okay, well, that kind of puts me back at square one, right? Remember that this we introduced linked lists here because when I had an array-based list, right, then the exact same thing happened, but it happened in the other order, right? So for example, if I'm always inserting an element at the end here, then this will be fast. This will be 0 seconds. Wow, it's even faster. So let's go back over here. Insert at the end here, 0 seconds. It's not even registering by the system clock. There we go, 0.001 seconds. Let's go up by an order of magnitude here, 10,000 seconds, 0.016, right? 100,000 here. Okay, now we're starting to see an issue, 0.5 seconds, and then order of magnitude up here, it's going to be maybe about 5 seconds. 2, 3, 4, 5.
Insert element at index linked list and not add element.
Because we originally did my array list, right? And we had add element, remove element, et cetera, and then we took all that stuff and put it up into an interface so that both of my lists implemented the exact same interface. So you have these methods, right, in both of those lists. Okay, this is getting too, this is probably because, come on, stop. Probably because of memory issues here. If I go over to my array list here and I change this so that we start out with 10, and then any time that we need to increase the size, where's that other 10? There we go. Let's go ahead and go up by, I don't know, 1,000. There we go. And it's going to run way quicker because we're not doing so much memory swapping and stuff like that. There we go. 5 seconds. That's what I expected. 5.11 seconds. So once again, we're seeing this kind of behavior where we go up by orders of magnitude. We're going up by 10 times as big, roughly 10 times as big, roughly 10 times as big. But it's the different operation. Insert at end ended up being extremely slow for a linked list. Insert at end ends up being what we would expect for an array-based list. What about this one? That's what we started out with, showing that, wait a second, an array-based list is actually kind of bad when you're always inserting at the beginning. If you're always inserting at the beginning here, then you'll see that kind of slowdown. Quick for 100, quick for 1,000, quick for 10,000 even, 0.2, there we go. I'll go ahead and put these down, 0.2, oops. And then 100,000 here, it's going to be 1, 2, 3, 4, 5, 6, 7. 100 times as slow, it's probably going to be about 20 seconds here. Right? And then, again, estimating, it's going to be maybe about 20 minutes. Right? I do want to see this. This is reasonable. There, 20 seconds, almost on the dot, right? It's almost like I knew what I was doing there, right? But if I kick this up to 1,000,000, it's going to be 100 times as slow. Why? Because we've got this behavior, 100 times as slow, 100 times as slow. Right? So why? Because we are always, at least with this array-based list here, to insert it at the beginning, that means that we're shifting things down. We're shifting 1,000,000 things down every single time we want to insert something at the beginning. We're not shifting anything down anytime we're inserting at the end. What about a linked list? Why is this fast now, inserting it at the start? Yeah, you're actually not even shifting anything. You're just creating a new node and putting it right here. New node, putting it right here. New node, putting it right here. Right? Because there's no array to shift. Why is it slow when you insert at the end, though? You have to run through the entire thing. And now here's the painter story. Right? This guy hires his, to paint his fence. And he says, okay, I charge $5 an hour or something. He goes, great, that's cheap. You're hired. So he said, he comes back an hour later and he's got half the thing done. Right? He goes, wow, this is only going to cost me $10. Right? He comes back another hour and he's got half of it done already, but then not as much as in the second hour as the first hour. Right? So he said, fine, maybe he took a break or something. Comes back a third hour, he has even less done between hour 2 and 3. And he goes, all right, well, it's still only $15. I'll come back an hour later. And he still has even less done in that fourth hour than he has in any of the previous hours. So he says, what's taking you so long? Why are you doing this? Show me how you're painting. He goes, okay. So he paints a little bit, right, on this area of the fence, walks all the way back to the beginning of the fence, dips his paintbrush into the paint, walks all the way back to where he's painting and continues. Every time he runs out of paint in his paintbrush, he walks all the way to the beginning of the fence and back and forth and back and forth, right? So do you see why it's taking him so long? Because he's spending more time walking back and forth than he is actually painting, right? At the very beginning it was fine. Why? Because he didn't have very far to walk. But towards the end, he's got further and further and further and further to walk each and every single time, which is why it goes from a 10 times as big, orders of magnitude, to 100 times as big. If I go from a behavior of n to 10n, right, I'm increasing an input size. And if my behavior is, say, n squared, and I go up to 10n squared, what does that equal to? 100n squared, right? In other words, if you increase the input size by an order of magnitude here, and your behavior of your algorithm or whatever you're doing is quadratic, then you are 100 times as slow. Gee, that looks familiar. Right? This is a quadratic algorithm. That's going to be a preview of what we're going to be doing in the next module. Before we get there, though, let's talk about some variations and finish up with this discussion. Right? So I'll just go ahead and cut and paste all of this. Here we go. There we go. So you can have also what are called doubly linked lists. And to show you a picture of that, I will just go ahead and not add them, but let's go with my iDrive over here. I've got some pre-canned pictures from my book. Here's a doubly linked list. Let me bring it over here. Right. So you keep track of the head and the tail, and not only can you go one direction, but you can go the other direction. That way, operations at both ends are efficient. Right? If you want to add something to the end here, that kind of takes care of the problem that we had right here. Right? Where if you want to add it to the end or to the beginning, if you're keeping track of both, you can do those immediately. Or you can traverse back and forth. Right?
Well, God help you if you try to insert in the middle.
Exactly. If you try to insert in the middle, you're back at square one, and you'll have that 100 times behavior here. Right? So there is no perfect data structure. If there were a perfect, the only thing that gets close is a hash table. But there is no perfect data structure. This is why we need multiple data structures. The solution is to shut off all your computers, then you don't have this worry at all, right? Go back to the Stone Age or something. Here's a circularly linked list, right? So I keep track of the head, but then I go next, next, next. I don't fall off the edge. Instead, I wrap back around to the beginning. This is great for, round robin kind of things, where you're going around and around, or a token ring network is what I usually say, but that's way too old. Nobody uses those anymore. Instead, what I'll use is somebody from my VR course. They're developing this game where they are going, they're going through different periods of time, so like the 70s, 80s, 90s, or whatever, and they've got this time gun where they shoot an object and then it goes forward 10 years. They shoot an object and it goes backwards 10 years or something like that. I think their example was, there's a piece of paper. You shoot it and it becomes a typewriter, right? You shoot it again and it becomes a computer. You shoot it again and it becomes a tablet. You shoot it again, then it goes back to being paper, right? And so they asked me, well, what's the best way of rotating through this? And I go, sounds like a circularly linked list to me, right? Why? Because instead of falling off, what do? You go back to the beginning, right? Yeah, go ahead.
Does that mean that inserting at the head would have to require going through the...
Well, if you keep track of the head, usually what you do is you keep track of the head and then the current, because there is no head. If it's a circle, where's this beginning of a circle? I don't know, an arbitrary value, or just keep track of a current that always goes around and around and around, right? It depends on what your use case for this is. And then you also have what are called unrolled linked lists. There we go. So instead of each node only containing one element, right? For example, over here my node was only holding one element here. You could change this so that you were holding an array of elements, right? And if you were doing that, it would look something like this. Say M, you're holding M elements here. So you've got the head, and that holds an array of M elements, and then that points to the next array that holds M elements. That points to the next array that holds M elements. This is kind of a hybrid between the two, right? Where you can store stuff in an array and get the benefits of random access, being able to jump to any location almost instantaneously. But also, you get the advantage that you can grow it without having to grow that individual array. You can go ahead and create a new array, right, and tack it onto the end or something, right? And then finding the balance here of the right M, that's the tricky part, right? Tuning that to your actual application or to general applications or something can be kind of tricky. Then you can take all three of these things and then combine them into one big giant list that's both circular, that goes back and forth, and that also contains an arbitrary number of elements.
Sounds complicated.
Oh yeah, each one of these features that you add gets even more complicated to actually implement, test, and make sure that it works. And then if you want to go the full 9 here, you can have what are called skip lists. And let me go ahead and just pull up an image here. So if you've ever been to a major city, you know that you can get on a subway, right, that goes from station 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8, 9, 10. That's called the local. It stops everywhere, right? If you want to go from, say, 1 to 10, though, right, do you want to stop at every single location? That'll take forever. Right? I want to go from 1 to 10 immediately without stopping. Well, that's not an option here. But what can I do? I could go ahead and get on the express that will take me from 1 to 2, stops at 4, stops at 6, stops at 9, get off, take the local over to 10. Right? Now, however many skips you've got, right? It's called a skip list. Why? Because this is skipping over 2 right here. This is skipping over 5. This is skipping over all the rest of them, right? Or this is skipping over 7 and 8, okay? If you go the full 9 though, and make sure that you're not skipping anything ever, right? Then you've got just a just a regular old linked list. If you've got every single possible relation, then you're back at square one with an array list, right? Just a more complicated array list. So those are all, there are lots of other variations as well, but those are doubly linked lists, circularly linked lists, unrolled lists, and skipped lists.
Yeah, we heard you like lists instead of arrays, so we put arrays in the list.
Exactly, and over and over and over again, right? All right, so let's look at list-based data structures instead of just lists now. And you've seen these before, stacks. What is a stack?
When you put a bunch
Of dishes on top of each other, right?
it's
Oops.
where it's being programmed in memory.
Program stack, right?
No, not
How, well, yeah, the call stack.
RAM is allocated.
The call stack, right? When you've got a function that calls a function, calls a function, calls a function, you're creating stack frames and putting it on the top of the stack. Every time you return from a function, what happens? It gets popped off the top of the stack so that you're back at that function call. More generally, it's just a stack of dishes, right?
Not to be confused with program memory, which is where the machine.
Well, memory is just memory. You can treat it as a stack, or the other thing is called a heap, right? Where it's larger, less organized, less efficient. But a stack here is way more organized. Now we're going to look at it as a data structure, though. Putting stuff in, this is the top of the stack, and this is the bottom of the stack. But there's really no orientation. This is just for, visualization purposes. You take your computer and you flip it upside down and nothing's going to happen. Putting something on top of the stack is called pushing.
It would probably not be good if
Oops.
turning the computer upside down just caused all the stacks to get.
Exactly. So you don't. It's what I'll eventually define here: a restricted access data structure. In other words, you're not going to be able to just do arbitrary operations, add to the end, add to the front, add at an arbitrary index. Instead, you always work at the top of the stack. You push things on top of the stack, or you pop them out of the stack.
Would there be any of the ones that are first in, first out rather?
We'll talk about that. That's a queue. That's its cousin. So 23, Jordan.
Yeah.
Let's go ahead and put him in. Right? He's now at the bottom of the stack. The stack was empty before, right? But 23 is now in there. Right? Rizzo. Let's go ahead and put him. Oh, I didn't circle him. There we go. Right. Let's go ahead and put him in there. All right. All right. What other famous numbers? Oh, here, Jackie. All right. Let's put him in there next.
What are you putting?
Oh, we don't know those numbers? Jordan's number? Michael Jordan? 23? The most famous number in basketball?
Basketball.
Okay. Well, Anthony Rizzo, you probably wouldn't know him because he was a Cub and then now he's a Yankee. 42, though, everybody would know him. Jackie Robinson? Right? Okay. So what order did I put them in? I put them in 23, 42, or sorry, 44, and 42. What if I start taking them out? Well, I'm not going to be able to take out an arbitrary object here, right? You can't take the dish out from the middle of the plates, right? Why? Because they all start falling. It's a restricted access data structure. You can only work from one end. So you can only pop out what's at the top of the stack. Right, there we go. Now that frees up 44 to be popped out. Now that frees up Jordan to be popped out. Make an observation. The order that things came in is the reverse order that they came out. That's LIFO. Last in, first out. Right? That's what a stack is. Right? Again, stacks are restricted access data structures. You're not allowed to just insert it in an arbitrary location. You're not allowed to retrieve from our arbitrary location. Right?
Allowed to sort things in?
Nope, you're shopping for a different data structure then, right? You don't want a stack because a stack is restricted in its behavior rather than its structure. Nope, I mean, I guess you could take everything out and then do something with it outside the data structure and then put them all back in, but that's a different operation. Collections such as lists or sets, these are a bit unstructured. They hold stuff. They might be sorted, right? You could sort them. Lists are ordered but not necessarily sorted. You can take a list that is unordered and then sort it. You can impose an ordering on it by sorting it, but it's a little bit different. Sorting imposes an ordering on the collection's state. Restricted access data structures impose an ordering on its behavior. You're only allowed to interact with it in a certain way. You can only push stuff on the top and pop stuff off the top, right? So it's not sorted. It's not ordered in any way other than the LIFO ordering, right? The only ordering, and I'll put that, I use that term very reluctantly, the ordering is LIFO. LIFO is last in, first out. There we go. Only two basic operations, push and pop, right? Push, you add something to the top of the stack. Pop, you retrieve and remove something from the top of the stack. There are some other operations here, but let's just go ahead and take care of those two. So I'm going to go ahead and take all of this out. Right? And let's go ahead and get rid of this. And I want a stack now instead of numbers, or instead of a list. So let's go ahead and create a new class, myStack. And I'm going to immediately parameterize it because I want this to be a stack of integers or strings or invoices, right? Not that you'll have a need for it, but I'll go ahead and keep it like this. Let's define the interface first. Public, void, push, an element X onto the top of the stack, right? So pushes, that is adds the given element X to the top of the stack. There we go. I don't know how we're going to do that, but let's go ahead and define the other one. Public T push, pop. Right? And let's go ahead and document that. Removes and returns the element at the top of this stack. There we go. All right. And we're going to have to figure that out because it's not compiling yet. Let's just go ahead and return null for now. And then don't forget to do. There we go. To do implement. Okay, now let's think about this. I don't want to reinvent the wheel. It's a list-based data structure. So what if we had a list of elements of type T that was private that we kept track of everything with? A list. What kind of a list, though? A list. All right. I'll just call it. I'll call it what it is. Stack. Right.
You need to know what's on the top and what's beneath the one on the top.
Okay. Well, you need to know where everything is, right? You need to keep everything, right? What if I had an array-based list, right? An array-based list would look something like this. It would have an array, right? There we go. Now, what if I just took this and, here, cut it, paste it, because I want to do something to it. Oops. There. Now, what if this is the bottom and this is the top? Well, not really. We just got done implementing an array-based list that automatically grew and shrunk. right?
No, there's usually a upper limit.
Wouldn't,
Well, only by memory, but yeah, go ahead.
wouldn't there be like the issue of if you add stuff that's bigger than the internal like array list size, that would cause more computational power over time?
It would, that's why when we were doing that demo, I went in there and I changed it from 10 to 1,000. Where was it? There. We're going, so that we're not, just a little bit each time, right? You can go ahead and tune this so that it's 10,000, right? And then that issue becomes less, and less. And then a different issue becomes more and more and more of wasted memory, right? So there are trade-offs. Right.
So I guess why would you use an array list instead of a linked list?
Good job. Okay, so you want to use an array, linked list instead. All right, fine. What is our bottom? And what is our top?
The bottom would be the last element, and then the top would be
Oh,
the
okay.
first element.
You want to do it this way?
Yeah, just because you can always insert at the top very easily, and then you can.
Okay.
at the top really
So this is the head right here.
Yeah.
Okay, I like that. Right? Why? Because now inserting at the top is just creating a new one, right? Efficient. We already witnessed how efficient that is, right? It grows very, very slowly. And if you're keeping track of the head, you can remove from the head very efficiently. I like that. But I'm not going to use my list because my list is not as good as, say, a Java linked list. Right? That's built into the language. What are you complaining about? Oh, duh. New. There we go. Then I can go ahead and import it. There. Now, super secret here. This linked list is even better than my linked list. Why? Because it keeps track of the head and the tail, right? And so it's more like, in fact, it goes both ways. It's more like where was it? It's a doubly linked list implementation. Right? So I get all those bells and whistles for free by simply using what's built into Java. Right? In fact, where's the actual node? Here's the node. Here's the node class. Let's take a look at it. Hey, how's it implemented? Let's go up to the top. Oh, sorry. It's an internal one. So there we go. Next and previous. It's a doubly linked list. And it stores an item. Instead of calling it element, they called it item of type E. Right? Looks familiar, right? That's exactly what we did, but with way more, features built into it. All right, then you tell me. Pushing something onto the linked list is what? This dot stack dot add
elements.
at a particular index 0. Right? The front of it.
Yeah.
Now, because it's doubly linked and it keeps track of both the head and the tail, is it like this or is it like this? It doesn't matter, right? As long as you are consistent about which end you work from. So, pop this dot stack dot remove and return the element at index 0. If you wanted to work from the other end, it would be this dot stack dot size -1 and this dot stack dot size -1. Which one is better? Zeros. Just keep it 0. Simple. Keep it simple, stupid. Right, there we go. Now let's make well, actually, I don't even need a constructor here. Oh, sorry. Return. There we go. Thank you. Now let's come over here and create my stack. I called it my stack, right? My stack s is equal to new my stack. And I should parameterize it for integers only so that I will say s dot push. Can I do arbitrary s dot add at index foo? No. Why? Because it's a restricted access data structure. Yes, under the hood, it's a full-on list, right? We could support any operation that a list supports, but that's not what we're building. We're building a new type of data structure here that restricts your access so that it enforces good behavior and efficient behavior. Push 10. push 20, 30, and 40. What does it look like?
Usually it's
I'm not even going to bother printing it. Oops. Ooh. Uh-oh.
back point is to store return addresses.
I wonder what that's going to do to OBS. There we go.
Yeah.
I accidentally hit the button that forced it to sleep. Let me make sure that OBS is still running. We're good. Okay. There we go. Sorry about that. Hopefully it works online. Anyway, I pushed 10, 20, and 30, and 40. I don't know what that looks like because I don't care, right? It's a restricted access data structure. What I can now do is say system.out.println s.pop. There we go. s.pop, pop, pop. Right? What's it going to print out? I put it in the order of 10, 20, 30, 40. When it comes out, it'll be reversed. 40, 20, 40, 30, 20, 10. Right? Uh-oh. What if you pushed 4 things and you try to pop 5 things?
Exception.
Let's find out.
Yeah,
Index? Size? What the hell are you talking about? This is a stack. Can I add something to an index? Can I retrieve something from an index? No. It's a restricted access data structure. So let's come back over here to my implementation and let's think about how we should handle that differently. What should happen when you remove from an empty stack? If this .stack.size is 0, then we know that it's empty. You ask for something that doesn't exist. One thing that I could do is what? Null, right? Then I get 40, 30, 20, 10, right? It doesn't throw an exception at all. This is old school C kind of stuff. We'll give you back a flag value to indicate that, nope, it doesn't, what, right? Except that what happens when you try to say, push not 10, but you say push null? How do you distinguish whether or not you pushed null and now you're just getting null back, right? That's not an error condition. Right? You push null, then 10, 20, 30, 40, then pop, 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 and at the very end, this is not an empty stack. You are pulling back, you are popping back null because you pushed it up there on line 11. Okay. So maybe we need if we're gonna go this way, then we probably need another convenience function here. Public Boolean is empty. Return this .stack.size equals 0. And then you can distinguish between, did I pull out null because I originally pushed it at some point, or did I pull out null because it was an empty stack and I shouldn't have asked for it? Well, now this gives me a way to distinguish that. Another way that you could have gone is throw an exception. Throw new illegal state exception, right? Empty stack. You asked for something that you shouldn't have, we'll throw it back to you and you handle it now. There we go. Throw an empty stack. At least it's not talking about indices anymore, which I have no idea what the hell you're talking about because I don't have a list here, I have a stack. Right? We don't want a leaky abstraction. If I'm going to go that direction, I probably want to say, I don't support nulls. If x is null, then no, you can't put null values on the stack. Throw new illegal argument exception. This stack does not support nulls. All right? And now an attempt to add null will result in that exception there. These are all design decisions that are up to you, right? How do you actually do this, right? Do I do it that way? Do I do it the other way? Maybe I have 2 different implementations. Maybe I have 2 different methods that one does one and then the other does the other, right? That has me thinking now, well, what could go wrong with, what else could go wrong with push here? You could impose like a, I don't know, a limit, right? Just like your call stack is limited to, say, 4 megabytes. What happens when you fill up the call stack and now you're trying to push one more thing Stack Overflow. We could enforce a Stack Overflow here by creating a private final int max size is equal to 100. And then any attempts to push something more than past its size, right? Else if this dot stack dot size is equal to 100, then throw new illegal state exception. Stack is full.
Size be something that's set with
I'm just showing this to you for examples of what you could do with this. If you were going to do something like this, I would make this into a private static final, right? Or I would say that's the default max size, and then an actual private static, or not static, but final int max size, right, that you take in at instantiation. Public my stack, this dot max size is equal to the default max size. That way, you can have another constructor that takes in an integer, int max size, and then use that. You could do a lot of things here. It depends on how you want to design it. Static makes it so that it's part of the class. Right? Final means that once you set, it can't change. Okay? So you've got a lot of other design considerations here. You can also have an optional peak operation, right? So what is peaking? Right? Your presents, your Christmas presents. You peeked inside of your Christmas presents? Yes? No? You tried to, or do you like surprises or you hate surprises? Right? So you peek inside of it, but you don't take it out, right? Because then you'd get in trouble. Right?
You just shake it.
You shake it. And, well, hopefully it's not breakable. Public T peak.
You don't just,
Get element at 0. There's what peak looks like. I will get the element at the top of the stack and give it back to you, but I will not take it off. So peaking means return, but do not remove the element at the top of the list. Again, we've got a whole bunch of other design considerations here. What happens when you pop from an empty stack? What happens, do you impose a capacity? How do you implement this stack? A linked list or an array-based list? You can do it with an array-based list efficiently, by the way. It's just that your end is the top of the stack. All right. So what about their cousins? A queue. Right. We'll save most of this for next time, but let's go ahead and, has anybody been down to Chippies?
you don't live how they have a word
No?
that only the first letter is the one that's pronounced.
Yeah. So the Chippies is the British British store. They've got a whole bunch of British candy and stuff like that. You heard of it? Okay. Anyway, we've gone down there because we like some of the candy that you can't get here. In fact, I was in Canada like 2-3 weeks ago, and I was like, I've got to get some Canadian candy, and so I shop around and start getting Canadian only candy. I'm like, these are just M&Ms with different shapes. Like, they've got all the same crap. So I ended up not buying any of that stuff. Anyway, what is a queue in British slang or British English?
It's essentially a line.
It's a line. A queue
First
is a line, right? And so you work at one end for one operation, right? You insert into the queue, and down here, then you take out from the other end, out. Right? Why? Because if you're lining up for, I use Dunkin' Donuts in Lincoln all the time because it's so near. You get in the line at Dunkin' Donuts, right? You're the next one being served, right? Here's 23, 44, and 42 here. Jackie got in line first, so who's the first one to be served? Jackie's going to be served first. Then who's the next one to be served? Well, it comes out of the queue and comes over here. All right? You go in order that you came into the queue. It's a line. There, that acronym is going to be FIFO, which is first in, first out. We do not want our lines to operate like stacks, right? The last person to show up is the first one that gets served. Their Dunkin' Donuts? No. The first one to show up is the first one that gets served. And you can imagine how we're going to implement this. How? A linked list, right? Where you work at one end or the other end depending on what you're doing. Or take it and flip it around and now you're doing the other operations at the other ends. In fact, you can take a queue and you can take a stack and you can combine them to make what's called a deck. Right? That's the ultimate. A deck. Yeah, why reinvent the wheel? You can just use a linked list, right? So a deck is a double-ended queue, right? Where you've got a queue, but you can work at both ends. Right? You can put stuff in, take stuff out at either end. That way, you can use a queue to simulate a stack, or you can use a deck to simulate a stack, or a deck to simulate a queue. You only need one implementation. And how you use it is up to you. Right? We'll pick it up there on Thursday, though. Your lab this week is exceedingly simple. It's only one method, putting an album into the database. So if you want to work on that today, great. Otherwise, work on it on Thursday when it's due.